This module is the sampling distribution of the sample mean. In the previous modules, we looked at sampling, descriptive statistics, probability, and the normal distribution. And while these topics seem very different from each other, we're going to put them together and lay the groundwork to move into inferential statistics, which is making an inference. So what I want to note here is that the emphasis is on not on learning to do some particular task, but more about understanding the concept of sampling distributions. I find that most of my students find this section to be a little bit out of place, and so if you keep in mind that what we're trying to do here is lay that groundwork and help you understand the concept, it will become much easier for you. We know that using a sample to get information about a population is preferable to conducting a census, and generally sampling is less costly and can be done more quickly. But because a sample provides data for only a portion of an entire population, we have to expect that there will be some errors. And I think it's pretty fair to say that a sample will provide data for only a portion of the entire population, and so we can't expect that sample to yield really perfect, accurate information about a population. And so, of course, this is the anticipation of a certain amount of error, and we call that our sampling error. And that is defined as the error resulting from using a sample to estimate a population characteristic. So let's introduce this with an example. For 2015, the mean tax of individual income returns was $10,319, and this was based on a sample of only over 200,000 returns from a total of 130 million returns. So let's just answer some questions about this. Identify the population under consideration. Well, the population in this situation is the 130 million returns. It is all of the tax returns is our population. The variable under consideration is tax, and is the mean tax reported a sample mean or a population mean? And since the mean was only taken or based on the almost 300,000 returns here, this is a sample mean. It's not a population mean. If we did it for 130 million returns, that would be the population mean. Would the mean for these returns equal the mean of all returns? So is this sample going to equal what the mean would be if we ran the whole census? No, it's not going to. We would anticipate that there's going to be some error. And so this leads us to our next kind of key fact here and definition, and this is the sampling distribution of the sample mean. So for a variable x and a given sample size, the distribution of the variable x bar is called the sampling distribution of the sample mean. And so what this really means is that the sampling distribution of the sample mean is the distribution of all possible sample means for samples of a given size. I know that doesn't make a ton of sense right now, but when we do an example, it will become more clear. So in statistics, we need to know that some terms and phrases are synonymous to each other. So for example, the sampling distribution of the sample mean is synonymous with distribution of the variable or distribution of all possible sample means of a given sample size. I just wanted to give you guys a reminder on some of the notation here. So the sample mean is x bar and the population mean is mu. We're going to do an example now to help you understand what we mean about the sampling distribution of the sample mean. So in this example, we have a population of interest that consists of 5 basketball players, and we're just going to call them A, B, C, D, and E. Now, the first part of this question is find the sampling distribution of the sample mean for samples of size 2. The next question is, make observation about sampling error when the mean height of a random sample of 2 players is used to estimate the population. And then C is, find the probability that X bar will be within 1 inch of mu. So in the next slide, we'll go through each one of these things in turn. But again, I just want to give you some context here. This is a population of 5 basketball players, and we're going to look at the data that we have on them of their height in inches. Okay, so first of all, we've got up in the corner player A through E, and we have their heights in inches. And the first thing that you should always do is calculate the mean, the population mean of this height, and you're always going to be using that later on. So as you're starting to go through these questions, it will be very important for you to start writing down things like the mean. So how do we calculate the mean? Again, mu is equal to the sum of x over, and you'll see it's a capital N because it's a population, and we're just taking all of these numbers here, adding them together, dividing by n, which is 5, and so we get a population mean of 80 inches. Okay, so this population is really, really small, and in A, they asked us to obtain the sampling distribution of all possible samples of size 2, and really what they're asking you to do is list all possible samples of size 2 as shown here. And again, this is without replacement. And so you guys have already done this a few times, and now we're starting to bring it back so that we can lay the groundwork for inferential statistics. So again, we have A and B. Start with A and B, AC, AD, AE. Perfect. And then you go to B, and will you go BA? No, because we already have an AB and we're not replacing anything. So we'll go BC, BD, BE, and we'll list them here, and we list their 2 heights, and then what they did is they took the mean of each of those heights. So you go down and down and down until you get to D, and obviously it's just D and E because we already have a DA, a DB, a DC, and we listed out the 2 heights there, and then we took the mean of those. So that is how we obtain the sampling distribution of all possible samples of size 2. And then it says to make some observations about this. So what we can observe here is that the mean height of 2 players probably isn't going to be equal to the population mean. So the population mean was 80. And these are all different sampling means based on the distribution of samples of size 2. And so from here, what we can say is that it is very likely that we are going to have some sampling error. The last part of that question asks us to find the probability that X bar will be within 1 inch of mu. And we can make a dot plot for that, and it's actually a very useful visual for us. So what they're asking us to do is they want to know how many of those sample means that we calculated from the sampling distribution of size 2 will be in 1 inch of the population mean mu. And if you recall, the population mean was 80. So we're going to put our population mean right here, 80. And then what we're going to do is we're going to put a dot for any of the other means that we calculated from our sampling distribution of size 2. And what we can see here is that there are 1, 2, 3 samples that have means within 1 inch of that population mean. So it's between 79 and 81 inches inclusive. So 3 of 10 are within 1 inch of that mean of 80, and so that is a 30% chance that the mean height of the 2 players selected will be within 1 inch of the population mean. Working off of the same example, we can continue exploring the sampling distribution of the sample mean. So in this part, we're going to use the same data, but we're going to obtain the sampling distribution of the sample mean for samples of size 4. And so what you can see here is that it's all the players again, A through E, and they've been listed, but it's in combinations of 4 without replacement. And you've got all of their heights here, and then those heights are used to calculate a sample mean. Now, the next part of this is to find the probability that your X bar will be within 1 inch of mu. And remember, mu was 80 in this situation. So we can do a dot plot here again, and you can see that all of the x bars located here are actually the dots here. So find the probability that x bar will be within 1 inch of mu. And if you look at it, there is an 80% chance that the mean height of the floor player selected will be within 1 inch of the population mean, because 4 out of 5 of them actually fall within that range. In this section, we're going to look at sample size and sampling error specifically. We're going to continue looking at the sampling distribution of the sample mean, and we're going to use the heights of the 5 starting basketball players to continue with the example. So what you can see here are 5 different dot plots, and these are dot plots for sampling distributions of the sample mean for the heights of the 5 starting players from samples of size 1, 2, 3, 4, and 5. And what this figure is really illustrating here is that the possible sample means cluster more closely around that population mean of 80 as the sample size increases. So you can see here n equals 5, and we're close to 80. Everything lands on 80. And as your sample size decreases, it spreads out more from there. And so this suggests to us that sampling error tends to be smaller for larger samples than for smaller samples. This is our key fact 7.1 on sampling size and sample error. The larger the sample size, the smaller the sampling error tends to be in estimating a population mean mu by a sample mean x bar. And what this really means is that the possible sample means cluster more closely around the population mean as the sample size increases. I've done a lot of research in my time as a professional biologist. One of the pieces of research I've been doing is growing mushrooms, not those kinds of mushrooms though. I've been growing certain types of mushrooms on biosolids, which is something that we can use for compost. But the compost or the biosolids are too high in heavy metals. So I'm growing mushrooms on them right now to see if the mushrooms will remediate out the heavy metals of arsenic, molybdenum, and selenium. But anyways, the reason I bring it up is because when we're doing research like this, we don't get to know the population mean. We generally don't know the sampling distribution of the mean either, but we can approximate the sampling distribution by a normal distribution. And so then we can use that to move forward and do some inferential statistics. So in this section, we're going to look at the mean and the standard deviation of the sample mean. I wanted to give you a reminder about some of the notation. So the mean of a variable is mu, and it is often subscripted if necessary with a letter that represents your variable. So for example, you might have the mean of x is written as mu subscript x. And the reason why I wanted to remind you of that notation or to let you know about it is because there is a very simple relationship between the mean of the variable x and the mean of the variable that is under consideration. So for samples of size n, the mean of the variable x bar equals the mean of the variable under consideration. So in symbols, we're basically saying that x bar is going to equal mu. So the mean of all possible sample means equals the population mean. Or in other words, for any particular sample size, the mean of all possible sample means equals the population mean, and this equality holds regardless of the size of that sample. Let's look at another example to help clarify what I've been saying here. So in this example, we are going to determine the population mean mu, and then what we're going to do is obtain the mean of all of the variables for samples of size 2. And then the final thing, and it's kind of in bigger font here, is to verify that mu x bar, which is our sample mean, is equal to the population mean. So let's verify that it's actually true. So to determine the population mean, which we've already done, mu is equal to the sum of x over n. Okay, so let's verify that the sum of all of our population, or our sample means, sorry, is equal to our population mean. So if you, even for samples of size 2, take all of these sample means that we have, and you take the average of those, what you'll find is that mu x bar is equal to 80 inches, which is the same as the population mean. And so the mean height of the 5 players is 80 inches. But let's take it one step further by applying this to samples of size 4 and then also verifying from here that the sample mean is going to be equal to the population mean. So we already know our population mean is 80 inches, and to obtain the mean for samples of size 4, we already did that in that previous example with the table that we had there. And so what you can see is that you take all of these means here, these sample means, and you add them together and divide by 5, and you're going to get 80 inches. And so it doesn't matter what size of sampling distribution you have. It can be 2, it can be 4, it can be 8, and the mean of that sampling distribution is going to be equal to the mean from the population. And so we can celebrate averageness in this because for any sample size, the mean of all possible sample means is going to equal the population mean. That's the simple relationship between the mean of the variable x and the mean of the variable under consideration. And it seems so easy. And it is. You will be asked questions on one of the assessments that will, basically state what the sample mean is and the population mean is. And if you have a population mean of 80, it's super easy for you because you know that it will be 80. Now we'll investigate the standard deviation of the variable x bar. So for samples of size n, the standard deviation of the variable x bar equals the standard deviation of the variable under consideration divided by the square root of the sample size. So in symbols, you can see that sigma x bar, or the standard deviation of your sample, is equal to standard deviation divided by the square root of n. So let's look at an example of this. Living space of homes. As reported by the U.S. Census Bureau in current housing reports, the mean living space for a single-family detached home is 1,742 square feet. So stop, write down mean 1742. Assume a standard deviation of 568 square feet. I would stop, write that down on the side. Question A. For a sample of 25 single-family detached homes, so on the side n equals 25, determine the mean and standard deviation of the variable x bar. And then it asks us to repeat it again for the samples of size 500. Okay, so let's do that. We know from our key fact that the mu x bar is equal to mu, and they've told us that the mean is 1742, so it's simply 1742. And to calculate the standard deviation, we'll apply this equation here, which is the standard deviation divided by the square root of n. They've given us the standard deviation of 568 square feet, and we have n as 25. So 568 over the square root of 25 is equal to 113.6. So the next part of this would be for you to do the next step with a sample size of 500. So what won't change is the mean. This is the same. It's going to be equal. But what will change is n, because if we're going to do 500, then we have 568 divided by the square root of 500. And you should try this out in your calculator, and you should get about 25.4. So we've already seen the key fact that states that the possible sample means cluster more closely around the population mean as the sample size increases. And so the larger the sample size, the smaller the sampling error tends to be in estimating a population mean by a sample mean. And these are the reasons why that key fact is true. The larger the sample size, the smaller is the standard deviation of your x bar. The smaller the standard deviation of x bar, the more closely the possible values of x bar cluster around the mean of x bar. And finally, the mean of x bar equals the population mean. So I do want to bring up the term, the standard error of the sampling mean. So in general, the standard deviation of a statistic used to estimate a parameter is called the standard error, or you might see it as SE of the statistic. Now we're going to move on to talk about the sampling distribution of the sampling mean for normally distributed variables. And so although it's not that obvious, a variable under consideration is normally distributed, or if it is normally distributed, so is the variable x bar. And you can prove this with mathematics, and you can prove it with simulations. But don't worry, guys, I'm not going to make you do the mathematics or the simulations to prove it. I trust that you trust me on that. So let's look at our next key fact, the sampling distribution of the sample mean for a normally distributed variable. Suppose that a variable x of a population is normally distributed with a mean of mu and a standard deviation of sigma. Then, for samples of size n, the variable x bar is also normally distributed and has a mean mu and a standard deviation of sigma divided by the square root of n. So I'm going to show you guys sort of the simulation to help prove that. And so what you can see here is they're looking at the variable IQ, intelligence quotients. And this is normally distributed and it's got a mean of 100. So that's why it's all of these are centered on 100 and there's a standard deviation of 16. Now, we can obtain the sampling distribution of the sample mean for different sizes. So for example, you can see in B, we've got size n equaling 14, and in C, we have size n equaling 16. So for the samples of size 4 that you can see in B, we have 16, which is our standard deviation, divided by the square root of 4, which is our n, and this equals 8. And so the sampling distribution of the sample mean is a normal distribution with a mean of 100 and a standard deviation of 8. So that's where that 8 came from. And so the possible sample mean IQs for samples of 4 people have a normal distribution with the mean of 100 and the standard deviation of 8. Now, for samples of size 16, so we can see that in C, we have 16 divided by the square root of n, or 16, and that gives us 4. And so what we can say here is that the sampling distribution of the sample mean is a normal distribution with a mean of 100 and a standard deviation of 4, or that the possible sample mean IQs for samples of 16 people have a normal distribution with a mean of 100 and a standard deviation of 4. And so what we're really trying to show here is how we can illustrate normal curves drawn to scale so that you can visualize two important things we've talked about. Both of our curves are going to be centered at the population mean, and of course, mu x bar is equal to mu. And the spread decreases as the sample size increases. So the spread is the standard deviation, and the sample size here is increasing, and so the spread is a lot less than with the smaller population size. This brings us to the central limit theorem, and this might be something you guys have already heard of. So if the variable x is normally distributed, so is the variable x bar. And this is a key fact, and it holds approximately if x is not normally distributed, provided only that the sample size is relatively large. And this is kind of an extraordinary fact if you think about it, and we do call this the central limit theorem. And you may be thinking, what's so extraordinary about that? Well, what's extraordinary about it is that for a relatively large sample size, the variable x bar is going to be approximately normally distributed, regardless of the distribution of the variable under consideration. So the approximation is going to become better with increasing sample size, but really, truly, we don't always need to have a normal distribution as long as we have a sample size that is large enough. And this may lead to the next question that you will have, which is, well, how do I know what sample size is good enough? And there will come a time later on where I will show you how you can calculate something like that. But it's, in research, samples of size 30 is usually pretty good. It's very close to being normally distributed in most cases, so we can use that. So let's talk about, summarization of the facts on the sampling distribution of the sample mean, and then we'll expand our knowledge a bit on it. And this is a summarization of the facts that we've learned about the sampling distribution of the sample mean. So suppose that a variable x of a population has a mean mu and a standard deviation sigma, then for samples of size n, the mean of x bar equals the population mean. The standard deviation of x bar is equal to the standard deviation over the square root of n. If x is normally distributed, so is x bar, regardless of the sample size. And if the sample size is large, x bar is approximately normally distributed, regardless of the distribution of x. I did playback on the last slide, and you can hear my dog groaning in there. So I'm going to post a picture of Scout, our lab instructor, onto our pet friends gallery so you guys can put a face to all the groans and yawns and licking that you might hear in the background. Anyways, I wanted to show you this figure here, and this is the sampling distributions of the sample mean for in the first part A, this is normal, and in B, this is reverse J-shaped, and then in C, it's a uniform variable. And so what you can see here is that basically, regardless of the shape that we have, or the sample size, really, the variable under consideration is going to be normally distributed, and the larger the sample size, the more closely it's going to look to normal. So you can see starting up here, this is just a small sample size, or the distribution of the variable. We've got an n of equals 2, so it's sort of normal. And this is the normal distribution, so it's fine. But this one here, this guy is a reverse J shape, and so it's getting to be a little bit more normal than you would see here, and the same with the uniform to the triangular shape. And then once you increase the sample size here to 10, you can see that they're starting to look even more normal. And then once you get down to 30, it's almost perfectly normal all through here. And this is really important when we're talking about research, because even if we have variables that are a little bit odd, as long as we have a large sample size, we can still run a lot of the inferential statistics that we use. This is the last sort of topic, and the only topic in this section that might be a little bit confusing or make your brain kind of work overtime a little bit. So let's look at it, because what it's doing is it's tying together a whole bunch of things that we've already done to make use of it in statistics. So we'll go through an example together. Birth weight. The National Center for Health Statistics publishes information about birth weights in Vital Statistics of the United States. According to the document, birth weights of male babies have a standard deviation of 1.33 pounds. So again, right on the side, standard deviation 1.33. Determine the percentage of all samples of 400 male babies, so n equals 400, that have a mean birth weight within 0.125 pounds or 2 ounces of the population mean. This is not the mean, okay? This is within this kind of distance from the mean. Interpret your answer in terms of the sampling error. So let's walk through exactly what we're doing here and what they're asking us to do. So first and foremost, we're going to use mu to denote our population mean birth weight of all of the male babies. And so we can just simply write that mu x bar is equal to mu because we don't have any other information right now to do anything. The next thing we can do is we can figure out what our standard deviation of that variable x bar will be by taking standard deviation, which was 1.33, over the square root of n, which was 400. So we can take 1.33 over the square root of 400, and we will end up with 0.0665. So this means that the percentage of all samples of 400 male babies that have mean birth weights within 0.125 pounds of the population mean birth weight of all the male babies is approximately equal to an area under our standard normal curve of mu plus 0.125 and minus 0.125 because we don't know the mean, but we know that we're looking for within 0.125 of that. And the other thing that we know is our standard deviation. So what we can do is say mu minus and mu plus the 0.125 over our standard deviation that we calculated will give us a z-score. So once we have a z-score, then what we can do is use table 2 to find the area under the standard normal curve that would equal between mu minus 0.125 and mu plus 0.125. So let's go through, calculate the z-score. So mu minus 0.125 is actually just equal to negative 0.125. And mu plus 0.125 is actually equal to just 0.125. And then you will take that over the 0.0665 that we have, and you get a z-score from negative 1.88 to 1.88. Now what it's really critical for you to do now is to take out table 2 and to find the area under the standard normal curve between the negative 1.88 and 1.88. And what you'll find is that it equals 0.9398. And so in the end, we can say that there's about a 94% chance that the sampling error made in estimating the mean birth weight of all male babies by that of a sample of 400 male babies will be at most 0.125.